So let's take a look at how to take integrals with trigonometric substitutions. And the idea behind this is the following. So we remember our Pythagorean identity, which is that cosine squared theta plus sine squared theta equals 1. And I can do a couple of things with this. So one of the things I can see is if I subtract sine from both sides, I will get 1 minus sine squared theta is equal to cosine squared theta. So that's one option. Second thing, if I divide through by cosine, I will get that 1 plus tangent squared theta is equal to secant squared theta. And finally, if I were to subtract 1 from both sides here, I'll end up with secant squared theta minus 1 is equal to tangent squared theta. And these three equations are what lead to the trig substitutions. So this one here shows me that if we have an a squared minus x squared being the variable part, in a square root or in a fraction. So this is going to help me with things under square roots or in fractions. Then I will let x equal a sine theta, because I'll end up with something that's going to end up being 1 minus sine squared, which will reduce. If I have this, so something in the form a squared plus x squared, that means that I will let x equal a tangent theta, because when I let x equal a tangent theta, I'll be able to reduce down to 1 plus tangent squared, which will let me get to secant squared. And if I have something like this, which is going to give me the variable squared minus the constant squared, then I will let x equal a secant theta. And for the same reason, I'm going to end up getting to something that's going to reduce to or factor to secant squared theta minus 1, which I can rewrite as tangent squared. So in order to do the trigonometric substitutions, first let x equal something based on one of these three. Second, you can find dx. Third, substitute into the integral. Fourth, you can find the antiderivative or find the integral. And finally, solve for theta in part 1. So I'm going to use this equation we had up here to get the answer. So this is the process. And the important things are these three formulas. It lets me know what to do to get started. So let's see a couple of examples. First, evaluate the integral of 1 over 16 plus x squared dx. And in here, I see I have the constant, this is sort of an a squared plus x squared. And following the rule we have here, when I have a squared plus x squared, I will use the tangent. So I see a is 4, because a squared is 16, so I will let x equal 4 tangent theta. Now, some people like solving for theta right away because we'll use it anyway, but I sort of do it at the end. We know that dx, the derivative of x, will be 4. The derivative of tangent is secant squared theta d theta. And this allows me to rewrite this integral as the integral of 1 over 16 plus, and I'll put this all in here for once. I usually sort of skip this step, but I'll have a 4 tangent of theta all squared times, and dx is 4 secant squared theta d theta. Now, reducing this down a little bit, I'll end up with the integral. I'll have 4 secant squared theta in the numerator. I'll have 16 plus 16 tangent squared theta in the denominator, all d theta. And I can take out a 4/16. Again, I would reduce that in one step here, but I'll show it so it's clear for everyone first time through where we get this stuff. I have a secant squared theta left over in the numerator, and I have a 1 plus tangent squared theta in the denominator. But looking back to our previous slide, I see 1 plus tangent squared theta is secant squared theta. So I can go ahead and rewrite this. 4 over 16 is the same as 1/4. Integral. Numerator is secant squared theta. Denominator is also secant squared theta, d theta. Those cancel. And so now I have 1/4 times the integral of 1 d theta, which is equal to 1/4 theta plus c. But here's the final problem. This is in terms of theta. The problem was in terms of x. So I go back and I look at this. This is the equation that relates x and theta. And I'll solve this for theta. So divide both sides by 4 and get that the tangent of theta equals x divided by 4. And take the arctangent to see that theta equals the inverse tangent of x over 4. And by taking this down here, I'll get finally 1/4 times the inverse tangent of x over 4 plus c. Okay, another example, and this is sort of the most annoying of the examples. I have the integral of 1 over y root y squared minus 49 dy. And I see y squared minus 49, it's in this form, x squared minus a squared, which, if we recall back here, if I have x squared minus a squared, I will let x equal a secant. I can see that a is 7 because a squared is 49, so I will let x equal 7 secant theta. And I need to, oh, sorry, it shouldn't be x. Let me fix that. Y equal 7 secant theta. And I need to replace the dy, so I'll find out what dy is. And the derivative of secant is secant tangent. And so I can take this information and plug it in and get the integral of 1 over y is 7, I'm going to need some more space on here, y is 7 secant theta times the square root of, and I said I'll skip the step here. I put y in here. 7 secant theta squared is 49 secant squared theta. I have a minus 49. And then I replace dy with 7 secant theta tangent theta d theta. Okay, so in here, I like getting all the constants out first, so I see I have a 7. I'll bring that out in the numerator. I have a 7 in the denominator, and I have both of these with 49s, so I can take that out. Now I'm going to write root 49 here. Again, it's another thing I would not do. I'd skip the step when I'm doing it, but I still need to take the square root of that 49 after I factor it out of these two terms. So, this one is the first 7. That's the second 7, and that gives me the root 49. And what's left over now is the secant theta tangent theta can multiply into the numerator. I have a secant theta in the denominator, and I'll have a square root of, and when I take out the 49, I have secant squared theta minus 1 d theta. And I see that secant theta cancels out. And I see a secant squared theta minus 1, and looking back here, once it loads, secant squared theta minus 1 is tangent squared theta. So I can rewrite this as, let's see, 7 times the square root of 49 is 7 times 7, 49. So I'll put this down here, 7 over 49. Integral of, I have tangent theta in the numerator. Secant squared minus 1 is equal to tangent squared in the denominator. And the square root of tangent squared is, it's actually the absolute value of tangent. There's some issues with that going on here, but I'm just going to say they cancel for simplicity's sake. This will work so long as we end up in the first quadrant. If we're in other quadrants, there'd be an issue. But if we're in the first quadrant, the square root of tangent squared is just tangent, and so these cancel. And now we're looking much better. We have 7 divided by 49 reduces to 1/7. Tangent divided by tangent gives me 1 d theta. And this will be sort of a common theme for a lot of trig substitutions, is we're going to end up taking the integral of 1. And so I get 1/7 theta plus c. And I have to do that same thing we did earlier. My problem had y's in it. I have a theta, so I need to take this original let statement where I connect y and theta and solve for theta. So if I divide both sides by 7, I'll get secant theta is equal to y over 7, and take the arcsecant or inverse secant, and I'll get theta equals inverse secant of y over 7, and put that in to get 1/7 times the inverse secant of y divided by 7 plus c. So those two were indefinite integrals. Let's look at a definite integral. In this one, we want to evaluate the integral from -1 to root 3 of 1 over the square root of 4 minus r squared dr. And I see that this is this a squared minus x squared format, which, looking back at this first thing, when I have an a squared minus x squared, I will let x equal a sine theta. So here, I will let r equal, a in this case is 2, so 2 sine theta. And when I find dr, because I will need to replace dr as well, the derivative of sine is cosine, so I get 2 cosine theta d theta. And if I'm going to change things from r's into thetas, I may as well change the limits as well. So this is a little bit different, a little different order than we had before. In that I'm going to solve this by dividing by 2 and taking the arc sine, and I'll have theta is equal to the inverse sine of r divided by 2, which means that when r is root 3, theta is the inverse sine of root 3 over 2, and the inverse sine of root 3 over 2 is, of course, pi over 3. And when r is negative 1, then theta is equal to the inverse sine of negative 1 over 2, which is, of course, negative pi over 6. So when I rewrite this, now I'm going to do the integral from negative pi over 6 to pi over 3 of 1 over the square root of 4 minus, and I replace r with 2 sine theta. 2 sine theta all squared is 4 sine squared theta. And then I replace dr with 2 cosine theta d theta. And I will bring out the 2 in the numerator. I will bring out the 4, which is square root of 4 in the denominator. And again, I would usually just bring out a 2 down there. And I'll be left with the integral from negative pi over 6 to pi over 3 of the cosine can multiply in the numerator, cosine theta, over the square root of 1 minus sine squared theta, d theta. And now, I remember 1 minus sine squared, as you see over here, is equal to cosine squared. So, I can replace this 1 minus sine squared with a cosine squared. So I get that's equal to 2 divided by root 4 is just 1. So I have the integral from negative pi over 6 up to pi over 3 of cosine theta divided by the square root of cosine squared theta d theta. The square root of cosine squared is, as long as we're in a reasonable quadrant, just cosine. So the cosine divided by cosine cancels. And we're left with the integral from negative pi over 6 up to pi over 3 of 1 d theta, which is going to be theta evaluated from negative pi over 6 up to pi over 3, which will then equal pi over 3 minus negative pi over 6. Pi over 3, in terms of a common denominator, is equal to 2 pi over 6 minus a minus plus. 2 pi over 6 plus pi over 6 is 3 pi over 6, which equals pi over 2. Okay, feel free to comment below with any questions, and I hope this helped out.